All right, everybody. In this video, I'm going to be talking about molecular polarity. Since we're not spending very much time on this in class, it might be helpful to you or some of you to see this lecture again, or to maybe reinforce some things that maybe you missed in the lecture. If you missed class altogether on the day that we covered this, this would be very helpful to you, I think. Okay, so what does it mean for a molecule to have polarity? It basically means this. Okay, one side of a molecule can have a slight electrical charge on either side of the molecule. Okay, just to give you a very simple analogy to this, you know that the Earth has poles, right? It has a North Pole and it has a South Pole. The North Pole is different from the South Pole, so the Earth has polarity, okay? It has poles. It has a North Pole and a South Pole. A molecule can have a slightly different, let's say, positive charge on one side and a negative charge on the other. In other words, it can have polarity. It can have a positive pole and a negative pole. Now, with a molecule, though, we're not talking about a full positive charge or a fully negative charge. We're talking about a partial charge. All right. I'm using a lowercase delta symbol to show a partial positive or a partial negative charge. So I'm going to write that out there. This symbol means partial positive charge. And this symbol means partial negative. Okay, so again, on one side of the molecule we have a slightly positive side, and then on the other side of the molecule we have a slightly negative side. If there's no polarity at all, there's no difference from one side to the other. Okay, so if I don't draw anything there, that would be a non-polar molecule. In other words, it has no positive pole or negative pole. It has no polarity. Okay, so let's take a look at a couple of examples of molecules. Okay, I think the best way to learn about molecular polarity is just to use some examples. Okay, so let's try some examples. All right, let's start with a molecule that I know has a lot of polarity, okay? And this is a really great molecule to start with. We're going to start with hydrogen fluoride, okay, HF. This will be our example 1. Okay, hydrogen fluoride. All right, if I was to draw this Lewis dot structure, it would look like that, okay? Now, the question that you're probably having right now is, how is it that a molecule is going to have more negative charge on one side than the other? In other words, how is it that a molecule can have polarity? Well, you might remember this term from earlier. Okay, so electronegativity, if you remember, it's the ability for an atom to attract a shared pair of electrons, in other words, a covalent bond, more than another atom. Now, if you were to look at the periodic table, you might remember that fluorine is more electronegative than hydrogen. Okay? So if I was to redraw this hydrogen fluoride molecule, let's just draw that pair of electrons there as the covalent bond. Okay? And I'll maybe circle that covalent bond in red. All right? So there's a covalent bond. Now, since fluorine has got stronger electronegativity, it's going to pull on those electrons more than hydrogen can pull on those electrons. And remember, electrons they exist as clouds around atoms. All right, so imagine this cloud of electrons spending more time around the fluorine. Imagine these electrons as a cloud of electrons living around that fluorine atom. Okay, they're going to be pulled more around the fluorine than they are around the hydrogen. Okay, fluorine has more electronegativity. All right, now this is going to give this molecule polarity. It's going to be more negative on this side, of the molecule than this side. Okay? All right, so I'm using that delta negative to show that this side of the molecule is slightly more negative on that side. It's got polarity. There's one side of the molecule is different than the other side of the molecule. One side of the molecule is a little bit more negative than the other side of the molecule. And you've probably heard me say this before, but so much about chemistry just simply has to do with positives and negatives, all right? Negative charges repelling each other and positive and negative charges attracting each other. You can really break chemistry down in many instances into just that, okay? Anyway, this would be an example of a polar molecule. Okay? What about a nonpolar molecule? How would that look? Okay, why don't we try, let's try a different molecule, okay? So this will be example 2. Okay, and this time we're going to go with carbon tetrachloride, okay? All right, carbon tetrachloride, if I do my Lewis dot structure, we'll have this. This is our Lewis dot structure for carbon tetrachloride, and you will probably recognize this to be a tetrahedral structure. So if this was my carbon, and this is chlorine, and this is chlorine, and then I have a chlorine coming out of the page and a chlorine coming, or behind the page and one chlorine coming out of the page. These would be my chlorines, and this would be my carbon, okay? All right, now, if you look at the periodic table, I think you will see that chlorine is more electronegative than carbon. Okay, so chlorine is more electronegative than carbon. So imagine this. We've got electrons being pulled toward that chlorine, electrons pulled toward that chlorine, and that chlorine, and that chlorine. My question would be this: is anybody winning the tug of war for electrons, right? Chlorine is pulling electrons on carbon all the way around this molecule. In other words, there is no one side of this molecule that's different than any other side. Okay? Nobody is winning the tug of war for electrons. All right? Really, the polarity, or there would be no polarity. There would be no polarity in this molecule. This would be a non-polar molecule. Nobody is winning the tug of war for those electrons. Okay? All right. So that's an example of a nonpolar molecule. No one side of the molecule has a more positive or more negative side. Okay? Let's try another example and see what we see. Okay? Let's try water. All right, so water, H2O. I'm going to draw my Lewis dot structure. We've seen this in class. There's my Lewis dot structure. Now we know that because of these lone pair electrons, that this molecule is going to get bent. Okay, I'm going to draw this differently now. There's H and H. Okay. If you look at the periodic table, from where oxygen is on the periodic table, you will see that oxygen is more electronegative than hydrogen. Okay, remember the trends that we learned. All right, when you will be expected to be able to tell what elements are more or less electronegative just by looking at the periodic table. And you should be able to do that. And I think if you look at the periodic table, you'll see that oxygen is one of the most electronegative of the elements. Okay? Anyhow, so oxygen, and I'll write this down, oxygen is more electronegative than hydrogen. Okay? All right, so what does that mean? All right, if I draw another ball and stick, I feel like ball and stick models are nice and simple. So here would be oxygen. Here is hydrogen. Here is hydrogen. Okay. In which direction are these electrons going to be shifted? All right. We're going to be shifting electrons toward the oxygen. All right? Electrons are going to be pulled toward oxygen. Now, listen carefully, because if this was a linear structure, this would be nonpolar, but it's not linear. Okay? We've got these lone pair electrons here, and we have these electrons being pulled toward oxygen. I'm just going to do my cloud like I did before. I'll make kind of a red cloud showing where electrons are getting shifted. Okay? Electrons are spending more time around the oxygen than they are around the hydrogen. Okay? All right, so that is creating a more negative side to this molecule and a more positive side on this side. The electrons are being pulled more toward the oxygen. They're spending more time around the oxygen, and that's creating a more negative side to this water molecule. Okay, so when you see water molecules, and this is going to be super important in biology, trust me. Okay, water molecules are like really extremely polar. Okay, so I really want to emphasize this. Water is an extremely polar molecule. It really makes water a very remarkable molecule. That might sound really weird, but for the size of water molecules versus their polarity, for such small molecules, they have extraordinary polarity. Anyhow, I really want to make a big deal out of that because I want to caution you against this. What if water was linear? What if it was? It's not. But what if it was? If it was linear, then electrons would be equally pulled toward the center on each side, and there would be no polarity. We know for sure that this water is extremely polar. It's very easy to test that. And in order for water to have the polarity that it does, we know that it's got a bent shape, not linear. All right. Let's try one more example at least. All right. Let's try another one. Okay. Let's try this molecule. This is called formaldehyde. You don't have to know that. You don't have to know that name. But this Lewis dot structure would look like this. Okay. All right. And if you're looking at this molecule by now, I'm hoping that you would recognize this as a trigonal planar molecule. Okay. Where this is carbon, and this is hydrogen, and this is hydrogen, and this is oxygen. Okay. All right, now, if you look at the periodic table, you should see that or recognize that oxygen is the most electronegative of these elements, okay? So within this molecule, okay, electrons are going to be pulled toward the oxygen side, okay? So this would be electrons being pulled within this molecule toward the most electronegative element in that molecule. If that's the case, then we're going to see a negative side to this molecule and a positive side to this molecule. And this molecule has polarity. We would say that this is a polar molecule. Okay, one more thing. One more example here. I would like to do this. Let's compare two molecules. Let's see which one has polarity and which one does not. Okay, these are the ones that I've got in mind right now. Okay, let's compare the polarity of boron trifluoride and nitrogen trifluoride, okay? First thing that we need are Lewis dot structures. Now remember, boron is an exception to our octet rule. So this would be the Lewis dot structure for boron trifluoride. And this is going to be the Lewis dot structure for nitrogen trifluoride. Okay. Now, when we look at these structures, let's define their shapes. Okay. Now, boron trifluoride, there is no lone pair at the boron. Okay. So this is going to be a trigonal planar shape. Trigonal planar. And nitrogen trifluoride. I'm going to spin this around because I like drawing these like this. Okay. We would have that kind of a shape. All right, now this is going to be trigonal pyramidal. Okay. All right. The question now is, do we have polarity in either one of these molecules? All right, now fluorine is very strongly electronegative. So let's take a look at how electrons are going to be pulled within boron trifluoride. they're going to be pulled equally all the way around this molecule toward fluorine. Remember, this is fluorine, 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 right? Okay, boron. Okay, so we're going to have equal pulling throughout. Equal pulling of electrons. Nobody wins the tug of war. Okay? Nobody's winning the tug of war. There's no one side of this molecule that is going to be more positive or more negative than any other side. Let's take a look at this molecule. Okay? So here we've got nitrogen and we've got fluorine, fluorine, fluorine. Okay. Now, in this molecule, because fluorine is so strongly electronegative, we're going to have electrons being pulled toward the fluorine, okay? But this structure is trigonal pyramidal, okay? So imagine this. Let's go with yellow. I'm going to shade in where the electrons are going to be drawn. They're going to be drawn more toward this side of the molecule, okay? Leaving this side of the molecule more negative and this side of the molecule more positive, okay? If this was a planar molecule, then, there would be equal pulling on all sides. It would be like this, but this is a pyramidal shape. So we have a concentration of electrons toward the bottom of this molecule, if that's the way you want to think of it. Okay. Around the nitrogen, electrons have been kind of torn away, and so the net effect is that we've got a negative side kind of on the fluorine side and a positive side on the nitrogen side of this molecule. Okay? So, if I was to draw like a basketball kind of a structure, we could say that in this basketball, we've got a stronger cloud of electrons down here and a weaker cloud of electrons up here, okay? And you could say then that this has got a positive charge to it and this has got a negative charge to it, okay? So the molecule has polarity. So shape really influences this a lot. That's really why we got into shape anyway, is because shape really influences the way that these molecules are going to act. Okay, I think that this is probably enough. So please don't hesitate to call me or visit me, or, if you have any questions, all right, email me. All right, thanks, guys. Bye.